Good morning, statistics students. Today we're going to go over the last topic in Chapter 6 that I'm going to ask you to learn. Your notes tell you when you're going to have a quiz on this stuff. So we're going to go over geometric random variables. They're related to binomial random variables, but there is a difference, and you need to know that difference, so you make sure you use the right formulas for a certain situation. So, on your sheet you got today, it should say 6.3 geometric random variables at the top. And here's the definition of a geometric setting. This is sort of like a binomial setting that you learned about with the bins at the beginning of the section. A geometric setting arises when you perform independent trials, that's similar to binomial, of the same chance process and record the number of trials it takes to get one success. This is the big difference. You just keep doing the thing until you get a success. On each trial, the probability P of success is the same. That is similar to binomial. You don't want the probability of success to be different from trial to trial. That's like doing something like picking a card out of a deck without replacement. Each trial, the probabilities change. So even if you could say, I'm picking a card until I get a 5, if you don't put the cards back each time you pick one, the probability of getting a 5 each time changes. So you do need to have independence. You need the probabilities of the success, whatever you define as success, to be the same on each trial, or close to the same. In the real world, you don't always know these exact probabilities, but the setting has to be such that on each trial you believe the probabilities are the same of success. So, this is the big difference here. What is difference with the binomial setting? The main difference is the number of trials, n, is not known at the beginning of the trials. So you do not know n at the beginning. Whereas in a binomial you do. You say, I'm going to, pick, well, you've had many examples. Roll a dice 10 times and see how many times I get a 5. That's a binomial setting, and the number of trials, which is 10, is known at the beginning. Taking a 10-question quiz, each question's a trial. You know there's 10 trials. But anyway, the geometric, you don't know that in the beginning. What is similar to a binomial setting are really the same. These are the other things. This is the n condition in the bins. But these other ones, BIS, are the same for binomial and geometric. In other words, it is binary. Each trial can be classified as a success or failure. There's not more than 2 outcomes, and one you call a success, and the failure is everything else. And as you guys know, sometimes success doesn't sound like a success, like testing positive for cancer or something. You can call that a success, and you just mean that's one group of outcomes, and all the others are failure, which is not testing positive. But then you can flip those definitions too. Anyway, binary means each trial can be classified into 2 categories, success or failure, and those 2 things are complementary. Independent means each trial is independent of the previous ones. In other words, whatever happened on the previous trial has no effect on the next trial. And success. The probability of success must be the same for each trial. That's what we talked about. You can't have an evolving situation. Or like the basketball example we did earlier in the section, where you have someone, or it's actually football was a good one, someone who kicks field goals. The conditions are different each time he kicks a field goal, because it happens from whatever point on the field where the 4th down forces them into the field goal. It could be at the 40-yard line, could be at the 20-yard line. There could be wind, there could be sun in the kicker's eyes, there could be all sorts of things. And so the conditions are different, which means his probabilities of success are different each time, even though success is getting the field goal and failure is not getting it. But that's a situation where the probability changes each time. But the success condition is you must have the same probability each trial of success. That's more like a basketball player standing at the foul line and shooting. The conditions are pretty repeatable. He or she's always standing the same distance from the basket under the same conditions with no defender right on them. And so it's a more predictable process that's being repeated. So that's what we mean. Here's examples of a similar problem in the binomial setting versus the geometric setting. I can say in a binomial, what if I roll a die 10 times and I record how many 6s I roll? So I could take this die. This is Claire's. Thank you, Claire. I will return your die someday. I could keep rolling it 10 times, record how many 6s I get, and you guys could calculate the probability of, say, getting 3 6s out of my 10. You guys know how to do that now. The geometric setting of a similar problem would be you roll a die until you get a 6. This is the key word here. When you see until or some word similar to that, it means you're probably dealing with a geometric setting and the probability formulas are different versus here where they tell you you're going to roll 10 times. This is the setup that's different. We're rolling a die and we're concerned with getting a 6. But in the first case, you're saying, I'm going to roll it 10 times and I'm going to see how many 6s I get. And your variable would represent the number of 6s you get. You can calculate the probability that that variable comes out, say 3, which is the probability that 3 out of 10 of your rolls will be a 6. In this case, you are rolling until you get a 6. You're going to learn how to calculate the probability of that, and your variable is going to represent the number of rolls it takes until you get a 6. So it's different. As you do these, you'll get used to that. Here are the, so this is about the setting up top, all this stuff. The bottom is the definition of a random geometric variable and what the probability calculation is if you have that situation. So we're going to use y, although in any problem you can use y, x, any letter, it's usually capital to represent both a binomial and a random variable. The main thing is you make sure you know which one you're dealing with so you do the probabilities correctly. The number of trials y that it takes to get a success in a geometric setting is a geometric random variable. So that's what we're defining. The probability distribution of y is a geometric distribution with a parameter p, which is the probability of success on each trial. The possible values of y are 1, 2, 3, ... Think about that for a moment. What we're saying, y represents the number of trials it takes to get a success. You could get lucky and roll a 6 right away if we're doing this example. That would take 1 trial. But you might take 20 rolls before you get a 6. That's probably not very likely, but it could happen. And that would be, you would be interested in y equaling 20, like how long, what's the probability that it took 20 rolls. But the idea is you're going to keep doing something till a certain event you're interested in happens. So y can take on lots of values. But when you're doing probabilities, you're usually interested in calculating the possibility that y takes on an exact value or a certain set of values. And here's how you do that probability. So the geometric probability formula, again, we're dealing with a geometric setting. We have a geometric distribution, and if the y has the geometric distribution with a probability of p successes on each trial, then the possible values of y are these, 1, 2, 3. It's repeating this definition. But if k is one of those values, so k represents it's similar to the binomial, but you're sort of saying, I'm just trying to figure out how long it takes to get that value, not that I'm doing 10 trials and what's the probability it came out a certain number of successes. So if k is one of those values, then the probability that y equals k is equal to this, 1 minus p to the k minus 1 times p. So this is your main formula that you're going to use for homework, although you're going to have some that you need your calculator for as well. I'm going to show you how to use this formula on the back. So here we go. This is an example to show you how this works. So we have a 4-sided die, and we're going to roll it until we get a 4. There's that word, until. So this is a geometric setting because we don't say at the beginning we're going to roll the die a certain number of times. We're saying we're interested in calculating a probability of how long it takes to get the first success. That's what geometric is. So we're going to let y equal the number of rolls till you get a 4. So before we go any further, you just want to realize that P is the same as what in the binomial. It's the probability of success on any given trial, and the probability of getting a 4 on any given trial is 1/4. So that's our P that we're going to use in these examples. It's 1/4. We don't know N, but the formula that we just looked at doesn't require that you know N. It just requires knowing P, and K is going to be the value that goes right here. So the first problem here is find the probability that y equals 3. We're going to use this formula that we just looked at and plug in. So 1/4 is our probability. That's going in for P. So the probability that y equals 3, what this means is it took 3 rolls to get before a 4 showed up. This 1 minus 4 to the 3 minus 1, I plugged in 3 for 3 for K. That's the first part, and then the second part is just times 1/4, not to any power. This is just 1/4 to the 1. So this equals 3/4 squared times 1/4. But what's really going on here is saying the first trial, you're doing 3/4 is the probability that you don't get a 4. So on the first roll, you didn't get a 4. That had a 3 and 4 possibility. Then on the second trial, you didn't get a 4. So that's another 3/4. That's 2 times. That's why that's a 2. But on the third time, you did get a 4. So that had a 1 in 4 possibility. So the 3/4 times 3/4 times 1/4 is saying the probability that the success happened on the third trial and you had 2 failures before that. That's why this is 3/4 squared times 1/4. It's failure, failure, success. That's what that means. If this had been 5, this would have been 3/4 to the 4th power. It would have been failure, 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 success. And since these are independent trials, you may remember from the last chapter on probability that you can multiply probabilities together if you know the events are independent and the trials are independent, and that's why this formula works. So, doing the math here, it's 9/16 times 1/4 equals 9/64, which in decimal form is about 0.1406. Now there's a way to do this with a calculator. This one's not that hard without just using the formula, but some of them would be hard or painful to do with without a calculator. And the function is called geomet, which is short for geometric, PDF or CDF. Just like that binomial, you're going to use PDF and CDF based on whether there's an equal sign or not. So since this has an equal sign, equals, you're going to use the PDF function just like the binomial, and you're going to find it in the same place. You're going to go into second function vars. Well, first you're going to turn on your calculator, and then you're going to go into second function vars and scroll down. You can scroll up or down. If you scroll up, you're going to actually go to the bottom of the menu, and there are your 2 geometric distribution functions. There's the PDF and the CDF. This one we want the PDF, so I'm going to choose that one. And it only asks for 2 values, P, which in our case is 1/4, 0.25, or 1/4. You can put in, if it's a probability that's not exact, put in the fraction. Scroll down, and then the X value. What do they mean by X value? It's this number, it's K really. All right, so you're going to enter, see I have it, 1/4, and then 3. That value is the number, the until number. Excuse me. We're saying, what if it took 3 rolls before we got the 4? So that's what you're putting there, is this number that's here. And then you hit enter, and this paste means you're going to stick it into the geometric function and hit enter again, and we got the same number we calculated by hand using the formula, which we should, of course. So that's how to do it on a calculator. Now, just like the binomial, you can find probabilities with less than or equal to or greater than. So you're just going to use the CDF function for that if you do it on your calculator. So let's look at this one. Find the probability that y is less than or equal to 3. That is the probability. Before I do it, I'm going to find the individual probabilities that y equals 1 and y equals 2. We already found y equals 3. The probability that y equals 1, using our formula, is 1 minus 1/4 to the 1 minus 1. This 1 is right here. 1 minus 1 is 0, so this is 3/4 to the 0. You may remember from algebra, anything raised to the 0 power is 1. So this is 1 times 1/4, which is 1/4, 0.25 in decimal form. The probability that y equals 2, these are numbers that y could be less than 3, is 3/4, which is our 1 minus 1/4, to the 2 minus 1 times 1/4. This is 3/4 times 1/4. This is because the first trial was a fail, which is a 3/4 chance. Second trial was a success, 1/4. That equals 3/16, which in decimal form is 1.1875. So the reason I did that is the probability that y is less than or equal to 3. Remember from what we did before that y can be 1, 2, 3, 4, etc. It starts at 1 though. So when we say less than or equal to 3, we're interested in these three outcomes, 1, 2, and 3. And since they're independent, you can add up their probabilities to get the overall probability. This is different, by the way, the multiplying, because we're interested in the combined outcome of all these trials. And then I got the success. This is saying it's this or this. This is an or situation. It's probability that y equaled 1, or the probability that y equaled 2, or the probability that y equals 3. These are mutually exclusive. I said independent. Sorry about that. So we can add these up because they are different outcomes with no outcomes in common. And here are the three probabilities that we just got. This one's here. This one is here. And this one up here is right here. That's the probability that y equaled 1, or the probability that y equaled 2, or the probability that y equaled 3, and those add up to 0.5781. That's decent odds, but that's hopefully not too surprising, because you with 4 only outcomes, the chance that you get a 4 in the first, second, or third try is around 0.57. You might say you would have expected that to come out 0.75, but that's not how this works. Because there's not just 4 possible outcomes. You could roll a dice 20 times and still not get a 4. So this distribution takes into account that it could take a long time to get a success. That's why this isn't as high as you think it might be, that after 3 rolls. Because there's a chance that you go a long time before you get that first 4. So anyway, that's our answer though. To do this one on a calculator, it's a lot like your binomial. You're going to do probability that y is less than or equal to 3, the same thing as here. But you're going to use geometric CDF. The reason we're using the CDF is when you have the less than or equal to, you use the CDF. Just like the binomial, you're going to find that in the same place. You're going to do second vars. I like to scroll up, and that takes me to the bottom of the list. Here's my CDF. I hit that. We're going to put in, I'll do 1 as a fraction this time, 1 divided by 4. Scroll down. We're interested in 3 being our equal sign, so it's 3 is our upper boundary because the outcome of 3 is included. Hit paste, and it's the very number we just got, 0.5781. So we're good there. Came out the same. Otherwise, if it didn't, it was a sign I did something wrong. Now, let's look at this last one. What's the probability that y is greater than 3? What this means is y could be 4 or 5 or 6 or 7. Or in other words, it took 4 or more rolls to get a 4. But you could, it doesn't stop at 4. You could keep rolling and rolling and rolling. This probability takes into account all the possible outcomes of taking a lot of rolls, basically, more than 3 before you ended up getting a 4. Theoretically, of course, it could take 100 rolls. That's not very likely, but it could happen. And this includes that. Now, you can't just add up a lot of probabilities for this because there is no upper limit on what y can be, although once you get beyond a certain point, the chances are extremely low that it took that many times. But you're going to use complements like you did with binomials because the calculator doesn't have this probability loaded in. You can say the probability that y is greater than 3 is the same as 1 minus the probability that y is less than or equal to 3. So we're going to make this switch that you guys learned how to make with the binomial. When you have a greater than, if it's strictly greater than, it's less than or equal to that number. If this was greater than or equal to, you would have put a 2 here. And then we already calculated this, right? We did it right here. And this goes here because we already did it. And you get your final answer. So that is it. I like these probabilities. Sometimes they're really interesting to calculate probabilities that something could happen, how long it takes before something happens. They are used a lot. And this is your introduction to them. And here's your homework. Thanks.